Okay, let's review the answers to this quiz. And this was a mastery quiz, so these really probed at whether you knew it exactly. It wasn't designed to be tricky, but they were difficult questions, I would say. So the first one, which may not have been your number one, but we're looking at this correlation between average sleep of U.S. men and average salary of U.S. Swiss women. So part of the issue is it doesn't make a meaningful connection, but there's a major statistical problem. And the correct answer here is that data on one variable must be paired with data on another variable. In other words, we could look at the average sleep and average salary of a group of people. So we would get, say, person number one, how much sleep they got, what their salary is. Person number two, how much sleep they got, average salary there. And then we could look for a correlation between the average sleep, between the sleep, not even the average, the sleep and the salary there, which may or may not be strong, but we could certainly run a correlation like that. The point is we need to be able to enter it into this, you can think of it as an XY pairing of values of these variables. Whereas here, say we have 100 US men and maybe 200 US women, there's no clear way how we're going to pair each man with a woman, and in that case, if we have different numbers, we couldn't even pair them. So we have to be able to pair the data with each other. The units definitely do not have to be the same to do a correlation. In fact, they usually aren't. The two populations are too different. That's not really an issue. We can look for a correlation as long as we can put them together. For example, if we were looking at wealth within a country and happiness, we could look at say we were comparing Mexico and United States. We could look at the happiest person in Mexico, or the wealthiest person in Mexico and the wealthiest person in the United States, get both of their happiness levels, and so on. Or we could do North Korea, for example. It doesn't matter how different the populations are. That's not an issue statistically. Amount of sleep would be completely independent. Even if it is, we can still run a correlation. That's not a statistical problem. That might be, and this is part of what I was trying to rule out by saying it doesn't seem to be a meaningful connection. But it's very possible to run statistics on two things that are completely independent and find out that there is no correlation. But that finding in itself is important, that the correlation is low or non-existent. So just because they're completely independent doesn't mean you can't statistically run a correlation, but the data does have to be paired. And that was the majority answer there, so that was good. Okay. Oops. Number two. So we had this article on how can rich people vote Republican and rich states vote for Democrats, which is kind of a little paradox, you might think. And most of you, I think, got this if you read the article. If variable A is correlated with variable B is correlated with variable C, it doesn't mean that A and C are correlated. In fact, they can be negatively correlated. So it really, one correlation with something correlated with something else, doesn't mean the other two things are correlated. So that is the correct answer. This was the biggest incorrect answer, the most popular incorrect answer. Wealthier U.S. citizens are more likely to vote Republican. This would be a good statement. Correlation does not imply cause, but it certainly wasn't the point of the article at all. And I think Ellenberg made that clear throughout the article that this is really the concept, this second one. This correlation is not transitive, is the word he used. That was the main point throughout the article. Number 3. So this one, again, the majority did get the correct answer, although also people chose other things. But appropriate use of the Pearson correlation. Here, height and weight. Again, we have a paired data point. So we have student number 1 out of 300. We get that student's height, that student's weight. We put it together in a pair, and so on. So we'd have 300 pairs. If you think Excel, that's 2 columns, each with 300 rows. And then we just run a correlation on them. So that certainly, and it's also height and weight, it would be reasonably linear for this group. Correlating age and height for the entire lifetime of a sample of 500 politicians. So here again, we have 2 data points on a sample. How is that different than this 4th one? Well, if you think about age and height across the entire lifetime, think about what's going to happen. Let age be on the x-axis, and maybe I should actually draw a picture of this if I can. Computer's very slow. So if age is on the x-axis and you think height, you're going to grow up and then you're pretty much going to stay constant most of the life, and then maybe even shrink a little bit at the end, depending on bone density. So it's not a linear relation. We're looking for something that's at least approximately a linear relation, or it wouldn't make sense to do the correlation. Even if we get an R value, it's not meaningful if the relationship between the two isn't linear. So in other words, as one goes up, the other should go up, which certainly isn't true for age and height across the entire lifetime. Correlating a man and his wife's data on height, weight, salary, education. Yeah, so this one I think the wording probably wasn't the best, because we could correlate a man and wife's data on height. Then we could correlate a man and wife's data on salary. So there'd be about 30 separate correlations we can run. My point here I was trying to get is if we, and even in this case, so I guess the wording doesn't matter, because we would have to have several men and their wives. We would have to have several couples, married couples. Then we'd have the height on each married couple, and that would be a correlation. Height of the husband, height of the wife, weight of the husband, weight of the wife. Each of these could be a separate correlation if we had a sample full of couples. But in this case, we just have a single couple, and we have their data on all these separate variables. So there's really no meaningful correlation here to run. And finally, political party. So the issue here, this is not a quantitative variable. To do a correlation, we need 2 quantitative variables, or at least something that can be, put on a number scale, which the political party cannot. So vaccines causing autism. So we're going to assume that vaccines do cause. So there's actually a causal relationship. Then which of the statements would be true? Let me see if I can. There we go. So positive correlations between receiving. So this would be a large data set. Each person, we would see whether they received vaccinations and whether or not they developed autism. Now you might say that this is a categorical, but this is different than a categorical because we can, if there's only 2 categories, we can consider one 0 and one 1, and that does allow us to run a correlation. So this, I think most people got this one, and also most people got that children would be more likely to develop autism if there indeed was a causal relationship. Now the biggest thing here would be there would be a negative correlation between receiving vaccines and developing autism. In other words, the more vaccines you received, the less likely you would be to develop autism. So this is directly opposite of what this first one is saying. In other words, you can't have both of these true. You're either going to have a positive correlation and negative correlation or no correlation whatsoever. But if the vaccines do cause autism, we would have a positive relation, not a negative. So this should not be selected. This third one was also, so this gets to the heart of what a causal relationship is. Just because something causes something else does not mean that it will cause it in all cases. So, for example, lung smoking causes cancer, and we know that. But not everyone who, what did I say? Smoking causes lung cancer. But not everyone who smokes develops lung cancer. Certainly, your rate or your likelihood of getting lung cancer is much higher, but it's no guarantee. And this sounds attractive, and I'm surprised that most of you picked this up, because I thought that more people would choose this. I'm really pleased that you didn't. So this is different because we would have the children, this would be a correlation, not a causation issue. So there'd be two groups of people, the children getting the vaccinations and the children not getting vaccinations. Those two populations could be completely separate. One could be all girls, one could be all boys. There could be many different factors that are different between those groups, and those other factors could be causing autism at a greater rate than the vaccines. So it's like apples and oranges here on D, two different populations. Okay, and finally we get to question 5. Okay, the reason why an experiment is so good is because of this random assignment. What the random assignment does, whether there's a control or just different treatments or multiple treatments, is that by randomly assigning the groups, we make sure that we balance the groups on every single variable you can imagine. Hair color, previous history with cancer, sinus issues, preference for heavy metal music, anything you can imagine, all the millions and millions of variables that could potentially affect an outcome. We're going to achieve balance on at least most of those variables, except there's one clear variable that we're not going to balance, which is the treatment itself. So if you're in this group, you get none of the treatment. Maybe this you get the full treatment. Maybe this group you get a partial thing of the treatment. But whatever it is, there's a clear difference between groups in the treatment you receive. So because it's balanced on everything else except the treatment, if you end up with a difference in outcomes, we can say that the treatment was actually the cause of the difference in outcomes. So that's the correct answer. And most of you got that. It was more some of these other issues. So why aren't these right? Pre-test and post-test, it is clear that the treatment caused. That's not true. So we could have, say, a group of, let's see, what would be a good example? The point is, we could have different groups where it's something totally different than the treatment that is creating improvement for the post-test. In other words, I'm trying to think of a good example off the top of my head. If we had SAT scores and one group took them their freshman year, then their senior year, another group took them freshman year, then sophomore year, but the freshman to senior also had a treatment involved, the freshman to senior group would improve a lot more, but it wouldn't be because of the treatment. The point here is your groups could be different on different variables, so this random assignment is really the key thing here. Higher sample size, you can have a huge sample size and still have very poor statistical results. There have been studies with over 1 million people who had very poor results because they weren't done well. And I think we're out of time there.